You know the routine. If you have questions, after you receive back your paper, first look at the posted key, because the key is posted. If you still have questions, see the person who graded the page on which the question, from which the question arises. Put that over here. Morgan Smith graded page 1, Lynn Pham page 2, and Tu Nguyen page 3. Then, if you're still not satisfied, see the supreme authorities. Unfortunately, that's me. I'll put the key up to bonus quiz 3 this afternoon. You should be bonus quiz 2. You'll be getting that back soon. And I will now begin to develop bonus quiz 3. As I would expect, you would expect. Now, back to the issue of developing a sound basis for rationalizing the strengths of Bronsted-Lowry acids, which we do in terms of assessment of effective negative charge density of the conjugate base of the acids. Because once we know something about the strength of a base, we immediately know something about the strength of its corresponding conjugate acid. Many factors apply. I remind you again, this is an issue of making good decisions, sound judgment. Because all the factors, after we finish assembling them, will be recognized not to apply to any case. All the factors will never apply to a single case. But a number of the factors will, in some cases. You have to decide which ones. First factor we looked at was charge to size ratio. Minus charge, large ion, minus charge, small ion. If no other factors apply, clearly the charge to size ratio is greater for the smaller ion. That makes the charge density greater. That makes the effective negative charge density greater. That makes the smaller ion a stronger base and its conjugate acid a weaker acid. Electronegativity. If no other factors apply, and the ions in question all bear a charge of -1, the ion derived from the atom of greater electronegativity will be the more stable, less reactive ion. The effective negative charge density will be small, or smaller, or smallest, depending on how many species to which you're comparing this. Upshot, a Bronsted acid that has as a conjugate base an anion whose negative charge density is effectively stabilized because of electronegativity will be a strong acid. Induction, an extension of the idea of electronegativity. Induction, in fact, shows you that highly electronegative atoms can exert their electron stabilizing ability through the covalent bond skeleton of a species. Induction in length of covalent bond. That reminds us that in order for atoms which have appreciable electronegativity to be able to stabilize negative charge density effectively, the atoms of appreciable electronegativity have got to be in the covalent bond skeleton of the species fairly close to the site, the location of the development of the minus charge. Orbital electronegativity. The greater the S character of a hybrid orbital, provided the orbitals are all derived from, provided the hybrid is derived from orbitals in the same energy level. The hybrid orbital with the greater S character will more effectively stabilize negative charge density, making the base weaker and the corresponding conjugate acid stronger. Resonance. Another way by which negative charge density can be recognized to be smeared throughout the covalent bond skeleton of a species. Greater the resonance, greater the degree of stabilization. One comment which I don't recall making regarding resonance, so we'll make it now. These anions each stabilize the single unit of minus charge by resonance. And of course I can rewrite this to show the double bond, which is not really a double bond over here, and a single bond over here, because these bond lengths and strengths are equivalent. Bond order is 1.5. True negative charge, true formal charge on each oxygen for this is -0.5 versus nitrate ion. No double bond in this, no single bond. Each NO bond has a bond order of 4/3. The true formal charge on each oxygen is -1/3. Well, the upshot of this is to remind us that nitrate ion is a weaker base than nitrite ion because of the degree of formal charge. -1/3 on each oxygen, -0.5 on each oxygen. But on what basis can we say this stabilizes negative charge by resonance more effectively than this, in addition to formal charge on oxygen? The answer to this lies on how many resonance pictures you can write. How many resonance pictures for this? In total? 2. This one? And this one. How many resonance pictures for this? 3. The more resonance pictures that are legitimate, the greater the degree of stabilization by resonance. I don't know that we made that comment. And of course you can see the obvious upshot of this, the reduction in formal charge on the peripheral oxygen atoms. For this, -1/3 versus -0.5 for this. PMO. Regarding PMO, principle of maximum overlap, which is a theoretical consideration. I asked you in regard to this to take a look at the table on page 2319, is it? Forget the page number. Was it 2319? See table. Is that table 3 or table 4? I think it's table 4. 4. Because there's an electron configuration table. As we noted in the conversation we had yesterday about PMO, rather than number of protons in the nucleus, what counts most regarding principle of maximum overlap is atomic size. Notice, if you will, when you look at the information in this table, that the bonds of hydrogen atom to other atoms are strong. Hydrogen's only got 1 proton in its nucleus, that's all. But hydrogen being the smallest atom means bonding electron density get closer to the nucleus of hydrogen atom than to the nucleus of any other atom. That leads to stabilization of bonding electron density. Now, how about electronegativity? Which atoms are the atoms of greatest electronegativity? Nitrogen, oxygen, fluorine, and chlorine. Well, if we think about fluorine, oxygen, and nitrogen, we're looking at atoms which are small atoms for period number 2, because as we go left to right, atoms are getting progressively smaller. So we shouldn't be surprised to find out that covalent bonds to nitrogen or oxygen or fluorine are commonly pretty strong. Not always. There are exceptions to this. We'll look at a couple of exceptions in a moment. But this is the kind of stuff to which principle of maximum orbital overlap relates. We'll look at a specific case in a few moments that I think will shed more light of understanding on this issue. So I'll not say anything more about that right now. We'll come back to it in a few moments. Solvation. Now notice this word. It's not salvation. That I do not how to provide to you. If I did, if I could, I would. But I don't know how to do this. Solvation. This is an effect which is much more important in the world of organic chemistry, because in organic chemistry, acid-base reactions are studied in all sorts of different solvents. Whereas in inorganic chemistry, most acid-base studies are done in solvent water. Sometimes other solvents, but usually solvent water. But to give you an idea of how solvation relates to Bronsted acid strength, we can consider acetic acid reacting in water, as we have done many times before. To make acetate-ion, where our measure of strength of acetic acid is the Ka value. Hydronium ion molarity times acetate ion molarity divided by HAC molarity. For equilibrium values, you know this. Now regarding the issue of solvation. A number of Bronsted-Lowry acid-base studies have also been done in ethanol as solvent. There's a formula representation for ethanol. You can write its Lewis structure if you wish. CH3 group, an intermediate CH2 group, and a right side OH group. So, what positive ion will I derive from ethanol if acetic acid behaves as an acid and protonates the ethanol solvent molecule as acetic acid solute protonated the water solvent molecule? We played this game back in chapter 18, you remember it? If you write the Lewis picture for this, you'll see non-bonding electron pairs on oxygen, and you'll see that the transferred H+ will glue to oxygen. And you'll make a species which formula-wise can be represented in this fashion. It would be more accurate if I put the plus on oxygen, because that's where the plus formal charge will reside. And the acetate ion. So if I want a handle on strength of acetic acid in ethanol, I go to the lab, make a solution of acetic acid in ethanol solvent, knowing the molarity because I prepared the solution, measure the concentration of this thing, and compare it to the concentration I get for hydronium ion with solute acetic acid being at the same initial molarity for each solution. The question is, will Ka acetic acid in water be the same as, larger, or smaller than Ka acetic acid in ethanol? This will give you an idea of how solvation relates to the issue. Now, before we answer this question, what's solvation mean? If you don't know what this word means, then we're rather talking about an exceptionally mysterious issue. What's solvation mean? What do you think it means? If a molecule is solvated, what's that mean? It's just a great mystery, the concept of which cannot be conceived. Are sodium ions and chloride ions solvated in water solution? I'm seeing heads go like this. Well, what's it mean? What does it mean to say sodium ions and chloride ions when sodium chloride solution is made, with water being the solvent? What does it mean to say that sodium ions and chloride ions are solvated in water solution?
They're solutes.
Well, we know they're solutes, but what does it mean to be solvated?
They're dispersed throughout solution.
Well, clearly they're dispersed, because the dissolving process tears apart the sodium chloride lattice, and the sodium ions and chloride ions are swimming about helter-skelter in the solution. Do the sodium ions and chloride ions interact with water molecules in water solution? Electrically? Here's a sodium ion. There's a chloride ion. Do the pictures like this because the chloride ion is a lot bigger than the sodium ion. Water molecule. Does the water molecule have an electric character? You're daggone right. It's quite polar. The hydrogen atom ends are squiggle plus, partially positive from an electron density distribution standpoint, and the oxygen atom end is partially negative. The bond moments are aiming from the hydrogen nucleus toward the oxygen nucleus, because oxygen is of considerably greater electronegativity than hydrogen. That accounts for why the water molecule is polar and shows these relative electron density distributions. Because all the electron density in the molecule is drawn toward oxygen because of its much greater electronegativity. So here's this molecule which has this electric character. Will this molecule tend to associate with this ion? Does this molecule have in part negative character? At the oxygen atom end. So will this end of the water molecule tend to stick to this thing? Coulomb? Isn't that right, Coulomb? Of course. That's what solvation is. It's a measure of the tendency of solute particles to electrically associate with solvent molecules. No more, no less. I mean, you got to think about what do these words mean? That's what counts. I don't know what you heard in 2045, but I always tell my 2045 class, more than once during the first couple of weeks of the gathering, in the first part of 2045, you're getting programmed with a new language, a language you have never spoken before. unless you spend time with mom and dad talking about atoms and ions and molecules and solutions and phases and phase changes and all that stuff, and I bet you didn't do it. When you are in chemistry class and you hear these words and terms, you got to know what they mean, because the chemistry class is being presented in this language. And if you hear this stuff and you don't know what the language means, then what you're hearing means nothing to you. If you read the chemistry book and you read these terms and words, I tell my students, whenever you come across a word or term when you're reading your notes or reading your chemistry textbook, and you see a word or term you haven't seen before, you don't know what it means, stop right there and find out what the hell the word means before you proceed. Otherwise, you're just getting your mind all boggled up. It's all based on understanding. Now, it's sad for me to say and realize that a lot of what's going on in 2045 these days does not depend on understanding. And that's what the hell's wrong with that course. And I'm doing everything I can to fix that. But we'll worry about that later. I'm sure you've come to realize that everything we do in here depends on understanding. That's it. Because that's where it is. That's what life depends on. If you intend to be successful at something which, in my opinion, is worth being successful at. You want to be a doctor doing an operation? And because you haven't learned or understood, during the surgery you say, I don't know what to do now. Let me go open the book. This person is dying. Because you don't know what the hell you're doing. Because you don't understand. Well, you know what the consequences of activities like that are. Think of all the brain power that went in constructing the space shuttle that at the tail end of January 1986 left Cape Canaveral. They had not made themselves aware of the consequence of low temperatures on the O-ring seals. You know what happened? The space shuttle exploded. And a lot of wonderful people died. Hey. These are all consequences of not understanding. We don't want to do that. So back to this. Solvation. A statement which refers to electric attractions between solute particles and solvent molecules. Sodium ion, chloride ion, which one do you think will be solvated more strongly on interaction with water molecules? They each have charge magnitudes of 1. This is +1, this is -1. Which of these do you think will be solvated more strongly?
Sodium.
Ion. Why?
Because hydrogen has a negative dipole. Or I mean water does.
Well, so what? Hydrogen, positive part of this dipole. The hydrogen atom ends of a water molecule will glue to this thing, and the negative end of the water dipole, the oxygen atom end, will glue to this thing. Why will sodium ions hydrate more strongly? Yeah. Tell me about the charge density. Which one has the greater charge density? Why? Yeah, that's why I do the pictures like this. Charge to size ratio? Hey. In terms of charge character, this is more plus than this is minus. Because the charge density of this exceeds the charge density of this. Okay? Now then, back to this. Because clearly these ionization reactions, clearly these reactions are ionization reactions. These reactions make from molecules, they make ions. Okay? So the answer to the question, Ka acetic acid in water versus Ka acetic acid in the ethanol solvent, is depending upon how effectively the products of these reactions are stabilized in the solution in which they have been produced. More to the point. Are these ions more effectively stabilized in water by solvation? Or are these ions more effectively stabilized in ethanol by solvation? In which of these solvents are these ions going to be more effectively stabilized? Which solvent? Really stuff you've done before. But now we're asking you to put it to use. Now we're asking you to understand this stuff. Because I know you talked about this stuff in 2045. But I keep telling those people, damn it, if you don't do chemistry with this stuff, it doesn't mean anything. That's not your fault. That's just me letting off a little steam. Well, in which solution will the ions be more, the product ions be more stable? Which molecule is more electric? Which molecule is more polar? Water or ethanol? Water. Hey, did you do an experiment on this? In Chemistry 2045 Laboratory Assignment 7 on solutions? You did that, didn't you? Or is that such ancient history? That's a bit of archaeological item which is so old and moldy you can't dig it up anymore. Hey, that's what solvation's about. Upshot, Ka acetic acid is much bigger in water than it is in ethanol. Because the product ions, which have to be stabilized in order for them to be able to form, at least in order to be able to form readily, are much more stable in the much more electric solvent. Okay? Now, as I said, since the solvent we're considering is strictly water, practically speaking, solvation is not really an issue for us at this stage of the game. But I added it in because it is part of the factors which relate to assessment of Bronsted-Lowry acid base strength. So what we've just found, acetic acid is a stronger acid in water than it is in ethanol by this kind of analysis. Now then, Part 9. You won't find Part 9 labeled as such in the notes. I'm going to invent it right now. Resonance PMO and species planarity. What considerations will you make for a species to find out that it is planar or not planar? What will you do? Well, you do a Lewis structure, that's for starters, that's for sure. And then what properties of the component atoms of the species in the Lewis structure will you look for to find out if the thing is planar? What is that? Non-bonding pairs. I think you better look beyond non-bonding pairs to find out if the thing is planar. Well, better yet, let's look at some cases, okay? We're going to page 2334. The first part, or first comments I want to make regarding 2334 is stuff that we don't really have to spend any time with, as far as I'm concerned. I'm going to write down the formulas. Since this is in the notes. The notes need serious rewrite. I'll get to it as soon as I can. I've been working on this rewrite now for about a year. I've got about 10 pages done. There's a hell of a lot more pages here than 10. It just takes time. Now, the acid strength trend for these acids is this. In fact, if you recall such, when you look at our acid-base table, we've talked a lot about water solutions regarding Bronsted-Lowry acid-base chemistry. where the solute acid is sulfuric acid molecule or hydrochloric acid molecule or nitric acid molecule. But if you look back at our acid base table, you'll see this is number 1 in the list. This is perchloric acid. It's the strongest common Bronsted acid which is known. It's also referred to as the strongest common mineral acid. Mineral means it's just derivable from minerals and natural materials that exist in Earth's crust. Okay? Now, on what basis can we recognize of these oxo acids? Oxo because they have oxygen in their composition, and the oxygen atoms for the conjugate base of the acid are on the periphery. Pardon me. One or more oxygen atoms for the parent acid molecule is on the periphery. Let me say that properly. For example, let's take a look at the extreme case. There's an abbreviated Lewis structure because I haven't included all the non-bonding pairs on the oxygens. But these are oxo-oxygens. They're on the periphery. This is not an oxo-oxygen. This is not a peripheral oxygen atom. Because this oxygen atom, while being bonded to the chlorine central atom, is also bonded to this hydrogen atom. So this is part of the skeleton of this molecule. I mean, they're all part of the skeleton. But this is not a skeletal atom. I mean, this is a skeletal atom rather than being a peripheral atom. Like this is a skeletal atom. Okay? What effect do these oxo-oxygens have? When this thing loses H+, minus H+, perchloric acid molecule does its acid thing. What effect do these oxo-oxygens have regarding stabilization of negative charge density? Do they help to stabilize negative charge density? On what basis? Is it one of the things over here? Which one of these things over here? Which one? How about that? Induction. Oh, here, induction. Right? Remember when we looked at trifluoroacetic acid, trichloroacetic acid, and acetic acid itself? And recognized that the reason why trifluoroacetic acid is the strongest acid of those three and acetic acid is the weakest is that these fluorine atoms exert a stabilizing effect on the negative charge, which develops when trifluoroacetic acid does its acid thing, loses H+, and becomes the trifluoroacetate anion. Right. We pointed out, if those fluorine atoms exerted no stabilizing effect on that negative charge, then trifluoroacetic acid, trichloroacetic acid, acetic acid itself would be the same strength. Because in each case, the negative charge developed on an oxygen atom, which was far removed from a molecular skeleton standpoint from these fluorine atoms in the trifluoroacetic acid molecule and from the chlorine atoms in the trichloroacetic acid molecule. But by seeing the big difference in strengths of those acids and corresponding degree of difference in degree of stabilization of negative charge density on the conjugate basis derived from those acids, we recognized, hey, fluorine atoms for trifluoroacetic acid, chlorine atoms for trifluoroacetic acid, those stabilize effectively the developed negative charge density. Well, how does the electronegativity of oxygen compare to chlorine? Oxygen's number 2, right? It's a lot of fun to think about electronegativity. Fluorine, oxygen, nitrogen. Chlorine's the same as nitrogen, practically speaking. But as we've noted, there are a hell of a lot more important molecules got nitrogen in their composition than those which contain chlorine. So I like the device to refer to, I like the device to be FON in regard to reference to electronegativity strength. Fluorine number 1, oxygen number 2. So when I create minus charge by this acid losing H+, these oxygens, in conjunction with the central chlorine atom, which also is appreciably electronegative, these provide a substantial stabilizing effect on this minus charge, making this a very weak base, which accounts for why this is the stronger acid. Here you'll only have 3 peripheral oxygens to stabilize negative charge by induction. Here 2, here only 1. So, after recognizing that when this molecule loses H as H+, I've got 4 equivalent oxygens, what's truly the minus charge, formal minus charge on each oxygen? Minus a 4th. It's pretty small. All right? So that, in brief, talks about oxoacids. Obviously, it must be something that contains oxygen. And for the anions derived from these acids, well, I have peripheral oxygen atoms, which by induction can stabilize negative charge density. Now let's get to resonance, PMO, and species planarity. I'm going to take away all the oxoacids except this one. Lewis picture. Write it. And add this one. In fact, if you wish, go directly to the conjugate bases of these acids. Respective Lewis structures for the conjugate bases. For this Lewis structure, for the chlorate anion, again, I don't care about its name because by just referring to this as ClO3 minus, that's good enough. Okay? Now, chlorine and nitrogen. How do they compare from an electronegativity standpoint? N and Cl. How do they compare?
Chlorine's 0.5 strong.
How do they compare? How much? 0.5. Where'd you get that information? Which periodic table? Yours? Let me see the periodic table you got. That hasn't got electronegativity values on it. Where'd you get this 3.5 for chlorine? That's not right. No. Most tables that I've looked at tabulate chlorine electronegativity as 3.0, some as high as 3.1. It can be argued that chlorine has a slightly greater electronegativity than nitrogen, which has an EN value tabulated as 3.0. We'll write this down, okay? You get rid of that 3.5 value you got there. That's wrong. EN, I'm going to take the Pauling value. That's 3.0. Same. Again, some tables will give the electronegativity of chlorine is 3.1. Somewhat ever so slightly greater than that for nitrogen. Okay? Now look at these two bases as things presently stand. In what ways are these bases similar? Well, they're each composed of 4 atoms. They each have 3 peripheral oxygen atoms. They each have a central atom of appreciable electronegativity, with the electronegativities being about the same. This one, we know, nitrate ion, does or does not stabilize negative charge density by resonance? Does or does not? Resonance applied to the nitrate ion? Absolutely. I can write 2 other equivalent Lewis pictures, neither of which will be right. Like this one isn't right, because the true NO bond length and bond strength, which has a bond order of 4/3, is shorter and stronger than NO single bond, longer and weaker NO double bond, right? But I can't draw a picture of that. I can't draw a picture of a part of an electron pair. How could I do it? I can't do it. But I can understand it and I can talk about it. That's what we're doing. And we're obligated to understand and talk about it because those are the properties exhibited by nitrate ion. And we have to do the best we can as students of chemistry to understand this and be able to explain it. Now let's look at chlorate ion. As things presently stand, for the single-bonded, exclusively single-bonded Lewis picture, the formal charge distribution is appreciable. -1 on each oxygen and +2 for chlorine. Can I conclude from this Lewis picture analysis as it presently stands that this thing also stabilizes negative charge density by resonance? Is that a fair conclusion? Can I write resonance pictures for this, the chlorate ion? Can I? Well, if we're going to write resonance pictures, we go to the atoms where minus formal charge is present and move non-bonding electron density away from that atom. That reduces that formal charge on that atom. So let's go to this oxygen. I'm going to take this non-bonding pair and do this. That will generate this. This oxygen is still -1, formal charge-wise, as is this oxygen. But the chlorine formal charge is now being reduced to +1 as opposed to +2. And this oxygen has had its formal charge reduced from -1 to 0. Which of these pictures do you prefer? And on what basis? Is this an acceptable Lewis picture? Well, we got the formal charges up here. We've reduced the degree of formal charge distribution, haven't we? But I ask, is this an acceptable Lewis picture? I see a head shaking no. Why do you say no?
Chlorine can't sustain more than 4 bonds.
Says who?
It can have an expanded octet because it's on.
What's an expanded octet? That's more textbook nonsense. You know what an expanded octet is? You paid 8 electrons on a balloon and then blow up the balloon. Expanded. What does that mean, expanded octet?
It can have more than 8.
Good. Well, more than 8, it ain't an octet anymore, is it? So to hell with this expanded octet nonsense language. That's not your fault. That's what these dumb books don't understand when they write this junk. An expanded octet is a blown up octet. An expanded balloon is still a balloon, right? Isn't it? It's blown up. So let's get more to the point and recognize that chlorine, which is an atom from period number 3, isn't it? Can make as many as how many covalent bonds? How many valence orbitals does chlorine have? How many valence orbitals does any period 3 atom have? We did this before. Now we're doing it again. Any atom from period 3. How many valence orbitals? How many? 9. Remember? 3s, 3p, 3d. 3s sublevel, single orbital sublevel, 3p, 3 orbital sublevel, and 3d, how many orbitals in that sublevel? 5. Well, 1 plus 3 plus 5 gives me 9. I can have as many as 9 electron pairs in the valence environment of any period 3 atom, I don't care which one it is. Because they all got 9 valence orbitals. Now, there are no known cases where a period 3 atom has as many as 9 valence electron pairs. But there are a number of cases where a period 3 atom has as many as 6. Some cases were 7. Let's write the formula for one which has 6. One you know about. One which is in our acid-base table. Does iron look familiar? Is this in our acid-base table? Is this an ion whose chemistry you've investigated by work in laboratory? Yeah, how about that? 6 coordinate covalent bonds. One between each water molecule and a central aluminum ion. And aluminum ion is derived from aluminum, period 3. So there's nothing wrong with this Lewis picture regarding number of central atom electron pairs. But that's okay, because I'm going to make a point of this anyway. Okay? This 4 limit to valence electron pairs for an atom holds for period 2. That's it. When you go past period 2, 9 valence electron pairs are possible. Now then, by recognizing that chlorine has these valence orbitals, I can reduce degree of formal charge separation for chlorate ion by rewriting the Lewis picture this way. Well, can I keep doing this and reduce formal charge distribution even more? Can I play this game? And now formal charge chlorine is 0. Formal charge this oxygen, 0. And now I only got 1 unit of formal charge. So I've reduced formal charge distribution considerably by speculating on resonance also being a property for this ion. Because I have written Lewis structures which are acceptable. No rule violation here. Okay so far? So now let's look at what we have regarding the strength of these 2 acids. Conjugate base this acid here. Conjugate base this acid here. We have seen they each stabilize the single unit of minus charge which they possess. By the presence of 3 peripheral oxo-oxygens, induction, a central atom of appreciable electronegativity, more electronegativity based stabilization of negative charge density. Oxygen atoms which, when we have played this resonance game, 0 formal charge. And this ion compares how size-wise to this ion? How will this compare size-wise to this ion? Will it be exactly the same size? Is chlorine exactly the same size as nitrogen?
Nitrogen.
How does chlorine and nitrogen compare?
Nitrogen is larger.
Which one's bigger?
Nitrogen.
Bigger than chlorine?
Chlorine.
Remember we coming down? Chlorine bigger. So if resonance for chlorate ion is as effective as resonance for nitrate ion. This should be the more stable base, because now I'm smearing the minus charge over a larger surface, because chlorine's bigger than nitrogen, which makes this ion in total a larger species than that ion. Okay so far? Now let's look at the facts. Ka this, a good deal bigger than Ka this. This is a good deal stronger acid. Why? You remember what I wrote over here? Resonance, PMO, and species planarity. Let's look first at the PMO part. The stronger the bonds at the bond sites where resonance applies, the more effective resonance is. That seems to be a fair statement. Do I expect to find stronger bonds between N and O or between Cl and O? Where should I expect to find stronger bonds? Between N and O and between Cl and O. Even though chlorine and nitrogen have about the same electronegativity. Where should I find the stronger bonds? N and O, ClO. Which one? N and O, why? What did this PMO business depend on? Did it depend on atomic size? Goody. Now, these are s orbitals. These won't be using s orbitals to make these bonds. P orbital for oxygen. P orbital for oxygen. What orbital does this thing use? To make pi bonds with oxygen atoms. How is this atom hybridized? sp2. But what orbitals is this thing using to make pi bonds with oxygen? This is sp2 hybridized. Okay? Well, if it's sp2 hybridized, then to make this hybrid for nitrogen, I've used its 2s orbital and how many of its valence 2p orbitals? sp2. How many did I use? How many valence 2p orbitals does this atom have? 3, right? And I used 2 of them to make this hybrid. So there's 1 left, isn't it? It's a p orbital. All right? Now tell me. This is a bad picture. Get this out. If p orbitals make pi bonds with other atoms that also use p orbitals, what kind of an overlap picture will I have? On your paper now, I want you to draw a picture of 2 p orbitals overlapped in pi bond fashion. 2 p orbitals overlapped in pi bond fashion. You seen this picture before? You have, haven't you? Is this an illustration of a pi bond involving p orbitals? What's the difference between a sigma bond and a pi bond in terms of overlap?
Sigma bond overlaps, like if you turn the dumbbells and you overlap the head.
One sharp, clear, direct statement. Difference between a sigma bond and a pi bond from an orbital overlap standpoint. What's the difference? Let me draw a picture of p orbitals overlap sigma.
Pi bonds overlap twice.
And sigma?
Bonds once.
Yeah, that's a difference. Several overlap regions. Pi bond, 2 regions of orbital overlap. Sigma bond, 1 region. That's the main difference. Now then, here's our internuclear axis. Here's a nucleus over here, here's a nucleus over here. Here's a nucleus here, here's a nucleus here. You see the sigma bond? The more stable is the sigma bond, the more direct is the location of this overlap region immediately between the nuclei. If it's immediately between, if this electron density for the sigma bond lies on this axis, which you can always draw to connect the two nuclei, that will give you the strongest sigma bond. But pi bond, you're looking for overlap regions, which becomes concentric about this internuclear axis. Okay? 2 overlap regions, only 1. Just for fun, you ever hear about delta bonds? No, I won't even write it down. Delta bond. Delta bond applies to the types of bond formation interaction d orbitals can make with other d orbitals. What do d orbitals look like? I'll bring some models in the future. You ever see or talk about shapes of d orbitals? A d sublevel is a package of 5 orbitals, this we know. And for the 5 d orbitals, there's pictures of these in the note, but for the 5 d orbitals look like 3-dimensional 4-leaf clovers. Like this. That look like a 3-dimensional 4-leaf clover if we imagine these not to be planar surfaces? You've seen 4-leaf clovers, haven't you? Ooh, that's a lucky one. 4-leaf clover. Okay. Well, if this is a d orbital on one atom, and I have another d orbital on another atom, which is here and approaching this atom. It's got another orbital, looks just like this. It's approaching this. Klump. How many regions of overlap will we have? You got another orbital that looks just like this. It's approaching this. Lobe here, lobe there, lobe there, lobe there. You get an overlap here, overlap here, overlap over here. 4 regions of overlap. That's a delta bond. Some chemists talk about these things with d orbitals. The difference is number of overlap regions. Okay? Now then, for the pi bonds in the nitrate ion, since nitrogen and oxygen are very close to each other in size, I can expect an orbital overlap diagram for the pi bonds in nitrate ion to look like this. Now, there's the p orbital on an oxygen atom for chlorate ion. If chlorine and oxygen do show some pi bonding with each other in this, the chlorate ion, what orbital or orbitals will the central chlorine atom use to make the pi bonds? Think before you answer. Tell me. Nitrogen, sp2 hybridized. How's chlorine hybridized? What is it? sp3. Wonderful. I repeat, if chlorine engages in any pi bond formation with the peripheral oxygen atoms for this ion, what orbitals will chlorine use? Can you use S? Can't make pi bonds with S orbitals. Can you use P? No. All the P orbitals are used in the sp3 hybridization, and S hybridization applies strictly to the sigma framework. So what's left? D. This look like it could make a pi bond? Here's a D orbital. Put a P orbital over here. Is that a pi bond? If I got 2 overlap regions? You betcha. But what's the difference? In terms or from the standpoint of PMO. How do you expect the size of a 3D orbital from chlorine to compare to the size of a 2p orbital from oxygen? Given that chlorine is a lot bigger than oxygen. pardon my artwork. The degree of overlap compared to the overall surface area of the orbitals is going to be a lot smaller here than it is here. PMO will not be as effective here as it is here, because chlorine and oxygen are from different periods, and chlorine's a fairly large atom. This aspect of PMO we talked about yesterday. Chlorine, much bigger atom than oxygen. 3d orbital, chlorine, a lot bigger than 2p orbital from oxygen. So PMO not nearly as effective. Now then, let's look at an additional aspect of these two anions. We recognize central chlorine atom sp3 hybridized, central nitrogen atom sp2 hybridized. What does that tell us about species geometry? What's the shape of this thing? Trigonal planar. What's the shape of this thing? Trigonal pyramid. Let's look at models. Isn't our model pretty? What do these loops simulate? What does this look like? Look like p orbitals? This is a model. Uh-oh. Get back. Where are you? Okay, there you are. This is a model of the valence orbitals for the component atoms of nitrate ion, which overlap with each other to make the pi system. Notice that these orbital lobes, because this species nitrate ion is planar, follows from its sp2 central atom hybridization. Planar. All these orbital lobes are mutually what? Parallel. Right? They're all mutually parallel. Well, we've drawn a picture of p orbitals overlap to make a pi bond. Did you recognize that in order for a pi bond to be strong and stable, the orbital lobes have to be parallel? Because otherwise, you cannot get effective overlap. The p orbital lobes have got to be parallel. All right? Nitrate ion. Now let's take a look at a model for the orbitals of a chlorate ion, which must overlap with each other if we're going to make an effective pi system for chlorate ion. What's the difference? This thing is not planar. This thing is trigonal pyramidal. Oxygen with p orbital, oxygen with p orbital, oxygen with p orbital. Central chlorine atom. I've drawn only one lobe. But I don't care what orbital or orbitals you imagine this atom uses, given that we've recognized it had to be a 3D orbital, or 3D orbitals to make pi bonds. There's no way we can have mutual parallel orientation of all these orbital lobes for the component atoms of chlorate ion to get effective orbital overlap. Point, can I get as effective resonance for chlorate ion as I can get for nitrate ion? No. That's what this planarity business means. Statement, and you're going to use this a lot in organic. In order for resonance to be a significant, appreciable property of a species, at the minimum, it has to be what? It has to be planar. It has to be planar. And it also has to have atoms which are how hybridized for organic molecules. sp2, so you got a p orbital remaining for this pi bond business. Planar and sp2 hybridization. That's what you're going to look for all the time for organic molecules. Planar and sp2 hybridization. Hey, so if you can write a Lewis picture and identify, from what you learned in general chemistry, identify hybridization, you'll know if the thing is planar. And you'll know, based on its hybridization, if it's got p orbitals available for pi bonding. So there's the difference. Chloride ion, not planar, not effective orbital overlap for the pi system, not effective resonance stabilization of negative charge density. So the fact that this base is a lot more stable than this base, this acid a lot stronger than this acid, is telling us resonance is important, because negative charge density stabilization proves itself to be a lot greater for nitrate ion than it is for chloride ion. And one other thing, well, no, we'll let that part go. Just leave it at that. So, planar, sp2 hybridization, effective strong pi system, effective resonance stabilization of negative charge density. This thing not planar. You can't have effective PMO, and you can't have effective resonance stabilization. Because of that, you can't have effective resonance stabilization of the negative charge density. We'll pick it up from this point tomorrow. Oh, wait. Papers.